Hello everyone. Today we are going to talk about Taylor's theorem and Taylor's series. So now why we are actually studying or talking about Taylor's theorem. So whenever whenever we are performing the analysis of real valued functions, a technique of approximation of functions with the help of polynomials is used. So Taylor's theorem does this job. So, so this is the tool which will provide you with the polynomial that will approximate a function fx under consideration. We can also call these Taylor's theorem as extension to mean value theorems. How? The mean value theorems, they relate the function fx with their first order derivatives, whereas this Taylor theorem relates the function fx with higher order derivatives. So let's see what is the statement of this theorem. So let fx be a continuous function having continuous derivatives up to n plus 1th order in some interval I such that there is a point A which belongs to this interval I. Now, why such a point? Then we have the Taylor's expansion of the function fx about point x equals to a as this fx is equal to fa plus x minus a into f dash a plus x minus a square f double dash at a upon 2 factorial plus x minus a to the power n upon n factorial fna plus rnx. Now this rnx is given by x minus a to the power n plus 1 upon n plus 1 factorial into n plus 1th derivative of f at some point c, where this c lies between a and x. And this Rnx is called as the remainder or error term of the expansion. So basically, in the left hand side, we are having a function which is continuous and having continuous derivatives up to order n plus 1. And on the right hand side, we can see that we are having a polynomial expression of degree n with some error term. Now we are calling it as the error term or the remainder term. So we mean that to this polynomial, if this error term is added, then we get the exact expression for the function fx. So now we will prove this theorem. Now, our main target is to find some polynomial Pnx, right? So we are in search of this polynomial. Now, so consider this Pnx as some C0, C1 into x minus a plus C2 into x minus a squared and so on till Cn x minus a to the power n. Now this is in our hand. Now, what are the conditions that this Pnx must follow? Firstly, the value of the polynomial at a must match with the value of the function at a. Then, if I take the first order derivative of this polynomial, substitute the point a, then it should match f dash a. So likewise, these things should match and so on. What should happen? That the nth derivative of this polynomial at a must match with nth derivative of f at a. So if Pna must be equal to f of a, so this will imply that C0 is equal to f of a. C1 is equal to f dash a. Continuing like this, what do we get? That n factorial into Cn is equal to nth derivative of f at a. So this will lead us where that this Pnx is nothing but f of a plus x minus a into f dash a plus x minus a ka square divided by 2 factorial into f double dash at a and so on, plus x minus a to the power n upon n factorial fn at a. So the function fx is approximated by this polynomial, and which is equal to this expression. Now, if I call Pnx as the approximation, this implies what? This implies that the difference Rnx is the Rnx, the error term is the difference between the function and the approximated polynomial. So this will imply that our function fx is nothing but Pnx plus Rnx, right? So now our target is to find what is this Rnx. This is not known to us, right? So let Rnx, the easiest choice, we expect it to be. So now here, this hx is not known to us. So we are to find this hx. So for this, here comes the trick, that somehow I'll define a new function and I'll call that function as auxiliary function. So what will I do? I'll define a function capital Ft as f of x minus what? Ft plus in the polynomial Pnx, replace this x by t. Sorry. In the polynomial Pnx, replace a by t. So this is what we obtain. X minus t f dash t plus x minus t to the power n upon n factorial fnt plus x minus t to the power n plus 1 upon n plus 1 factorial into hx. And where does this t lies? T lies between a and x. Now, certain properties that are followed by this capital F. First is that f of t is continuous in this closed interval. Secondly, f of t is differentiable in the open interval. We can very well see that this capital Ft is differentiable in the open interval and it is continuous because this is a polynomial. So polynomials are continuous and fx is a function which by hypothesis was continuous. So ft is continuous and ft is differentiable also. Further, we observe that f of a is equal to 0 and f of x is also 0. So, so then comes, so what we observe, a function which is continuous in a closed interval. It is differentiable in the open interval. And at the endpoints of the interval, the value of the function is 0. So, something called as Rolle's theorem comes to our rescue. And how does this rescue us? So this Rolle's theorem ensures that there exists some C belonging to this open interval Ax such that f dash C is equal to 0. So this will imply what? If I differentiate this f dash t, what do I get? F dash t minus f dash t plus x minus t f double dash t minus 2 into x minus t upon 2 factorial f double dash t and so on plus x minus t to the power n factorial f n plus 1 at t minus n plus 1 into x. So this ultimately is equal to x minus t to the power n upon n factorial into hx minus f of n plus 1 of t. So this implies what? That our hx is equal to the nth derivative of f, n plus 1th derivative of f at c. So our Rnx is given by x minus a to the power n plus 1 upon n plus 1 factorial into f. And this completes the proof of the theorem.